Let's try to prove now that T of n is in big omega of n to the power log base b of a times log to the power k plus 1 of n. So we need to prove this, which is equivalent to proving that T of n is bounded from below by some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. This is what we need to prove. So let's start from the expression for T of n, the familiar expression which we've seen several times now. T of n is n to the power log base b of a multiplied by T of 1 plus the summation of I equals 0 to h minus 1 a to the power I times f of n by b to the power I. These are the costs associated with the leaves of the recursion tree. These are the costs associated with the non-leaf nodes of the recursion tree, summed up level by level. Now, in the generalized version of case 2, we are given that f of n, okay, we were given that f of n is in theta of n to the power log base b of a times log to the power k of n, where k is some constant greater than or equal to 0. This is what we are given, and this is what we need to prove. So based on this given information, we can say that f of n is sandwiched between two constant multiples of this function. We actually looked at that here. There exist two constants that are greater than 0 such that f of n is sandwiched between those two constant multiples of n to the power log base b of a times log to the power k of n. So in a previous video we saw this, and in trying to prove an upper bound on T of n, we relied on the second inequality. Now in trying to prove a lower bound on T of n, we are now going to rely on the first inequality. So focusing only on the first inequality, we are given that f of n is bounded from below by some constant multiple of n to the power log base b of a times log to the power k of n. So since we are trying to achieve this as our end goal, if we start from T of n being equal to this expression, if you think about it, we'll need to do the reverse of what we did in the previous proof when we proved an upper bound on T of n. In trying to prove an upper bound, we replaced this f of n divided by b to the power I by something larger than this function, and thereby obtained an upper bound. This time we are relying on the first inequality because we are going to replace f of n by something smaller than it. We're going to replace it by the right hand side of this inequality, which gives you a lower bound on f of n. So we are going to replace this f of n by b to the power I by its corresponding lower bound, and thereby we will reduce the value of this expression overall, thus making it less than or equal to T of n. So that will hopefully take us a step closer to proving this kind of a claim. So if f of n is given to be bounded from below by a constant multiple of this function, let's see what inequality we get for f of n divided by b to the power I, because what appears in this expression is f of n divided by b to the power I. So let's substitute n by n divided by b to the power I everywhere in this inequality. And what we'll get is this inequality. F of n divided by b to the power I is greater than or equal to c1 times n divided by b to the power I, the whole thing raised to the power log base b of a, multiplied by log to the power k of n divided by b to the power I. So let's take the right hand side of this inequality. This is something which we are given. So let's take this right hand side of this inequality and replace this f of n by b to the power I by this right hand side. By doing so, we'll be reducing the value of this term. So we will obtain something that is less than or equal to t of n. This expression was equal to t of n, and by reducing this second expression, we'll get something that is less than or equal to t of n. So t of n will be greater than or equal to the resulting expression. The first part of the expression is the same, n to the power log base b of a times t of 1. The second part of the expression has this substituting for this. Right? So all we've done is we've substituted the right hand side of this inequality over here. Now we can simplify this by taking c1 out of this summation, because it's independent of I. We can also take out n to the power log base b of a outside the summation, because this is also independent of I, and we'll be left with a to the power I. We'll also be left with b to the power I, the whole thing raised to the power log base b of a inside the summation. And here I've actually interchanged the powers, because just as we did that in the previous proof, we'll do it here so that b and log base b cancel each other out, and we'll be left with a to the power I here, which will cancel out with the a to the power I in the numerator. And then we'll be left with log to the power k of n by b to the power I. So this term is cancelling out this term. The only thing that will be left inside the summation is log to the power k of n by b to the power I. So t of n is greater than or equal to this first expression plus c1 times n to the power log base b of a multiplied by this summation. Now notice that we've moved some steps closer to achieving this on the right hand side. We have a constant multiple of n to the power log base b of a, but we don't yet have log to the power k plus 1 of n. We have this summation over here. Now if you're able to prove that this summation is greater than or equal to some constant multiple of log to the power k plus 1 of n, then we will be able to substitute that constant multiple of log to the power k plus 1 of n in place of this, and thus get something even smaller than T of n. And hopefully that'll that'll bring us closer to, even closer to this goal of proving that some constant multiple of this function is a lower bound on T of n. So I've copied the same expression from the last line of the previous page here. We'll be focusing only on this summation here, and we'll try to prove that this summation is greater than or equal to some constant multiple of log to the power k plus 1 of n. Because if we can prove this, then we can take this and replace this box by c times log to the power k plus 1 of n. And we'll get T of n is greater than or equal to this term plus c1 times the function that we wanted. The function that we wanted here. So how do we go about proving this? Well, if we expand this series, the first term of the series is log to the power k of n. That's the term we obtain by plugging in I equal to 0. B to the power 0 is 1, so the first term will be log to the power k of n. The second term will be log to the power k of n by b to the power 1. That's for I equal to 1. And so on. The third term will be log to the power k of n by b square. And the very last term will be log to the power k of n divided by b to the power h minus 1. The last term can be obtained by substituting I equal to h minus 1 here. Now this argument of the log function in the very last term, n divided by b to the power h minus 1, this is nothing but b. And that's because b to the power h is equal to n. Why is that? Because from the recursion tree, we've discussed this earlier, but in the recursion tree, n by b to the power h is the size of the subproblem at level h. And if h is the height of the tree, n by b to the power h must be equal to 1. This is how we obtained the fact that h is log of n to the base b. So if we plug in b to the power h in place of n, we'll get b to the power h divided by b to the power h minus 1, which is b. So this shows that this series, if you look at this series and if you focus on the arguments of the log function, the arguments are going down, starting with n, then becoming n by b, then becoming n by b square, and so on. So decreasing by a factor of b in every term, and in the very last term, the argument becomes exactly equal to b. The number of terms in this series is equal to h, because you start with I equal to 0 and you end with I equal to h minus 1. So the powers of I here vary from 0 to h minus 1. So there are h different terms. And we know that h is log of n to the base b. So in trying to prove that this series is greater than or equal to some constant times log to the power k plus 1 of n, we need to somehow obtain log to the power k plus 1 of n here. The first term has log to the power k times n. Now if every term was log to the power k of n, we would have obtained this, because then log to the power k of n would have been multiplied with h, which is the number of terms, and we would have gotten an extra power because h is log of n. So this would have been log to the power k of n times log of n. But we can't do that, because by replacing these arguments by n, you're getting something larger than this. What you need to do is to actually make this series smaller and still have it bounded from below by log to the power k plus 1 of n. So as a step towards that, let's look at the middle term of this series. The middle term of the series is the value at approximately I equal to h by 2, because we are starting with I equal to 0 and we are going approximately up to h. So let's say that the middle term is around I equal to h by 2, and the middle term will be log to the power k of n divided by b to the power I, but I is h by 2, so it will be b to the power h by 2. Now we know that b to the power h is n, so b to the power h by 2 is basically b to the power h, the whole thing raised to the power 1 by 2, and b to the power h is n, so this becomes the square root of n. N divided by the square root of n, of course, is the square root of n. So this becomes log to the power k of the square root of n, which can be written as log of the square root of n, the whole thing raised to the power k. So the first term was, the second argument was n by b, the third argument was n by b square, the middle argument was the square root of n, and the last argument was b. We can simplify this further. Log of the square root of n, the whole thing raised to the power k, is equal to half of log n, the whole thing raised to the power of k, which is equal to 1 by 2 to the power k multiplied by log to the power k of n. So this is the middle term. The terms to the left of the middle term are larger than the middle term, and the terms to the right of the middle term are smaller than the middle term, because the arguments of the log function are decreasing down this series. They are decreasing from left to right. So everything to the left of the middle term has an argument which is larger than the middle term. So all the terms to the left are larger. And all the terms to the right of the middle term have smaller arguments than the middle term. And so they are smaller than the middle term. I've shown this diagrammatically here. So this is the middle term at I equal to h by 2, which we simplified to 1 by 2 to the power k times log to the power k of n. These terms are larger than the middle term, and all these terms are smaller than the middle term. Now remember that we are trying to somehow prove that this series is greater than or equal to some constant multiple of log to the power k plus 1 of n. We're trying to prove that this series is greater than or equal to some constant times log to the power k plus 1 of n. And we already have this log to the power k of n appearing in the middle term. So if we replace all the terms that are larger than the middle term, namely these terms on the left, by the same argument as in the middle term, right? If we change this n to n by b to the power h by 2, if we change this n by b to n by b to the power h by 2, and so on, if we reduce all these arguments down to the argument in the middle term, we will be reducing the value of this summation of this series. Now, why do we want to do that? Because if we reduce the values of all these terms to the value of the middle term, how many terms will we have whose value is equal to 1 by 2 to the power k times log to the power k of n? We will have about h by 2 terms, all with the value of log to the power k of n times 1 by 2 to the power k. And h, of course, itself is log n. So if we add all these terms, we need to, the summation will have a value equal to this term multiplied by h by 2 plus 1. So what we're going to do is, we will take these larger terms, replace each of these terms by this term, by the middle term, which we know has this simplified value. And by doing so, we will get something smaller than this series. So note that this middle term over here is depicted as it is over here, and all the terms that are larger than the middle term to the left have been changed to 1 by 2 to the power k times log to the power k of n, which is the value of the middle term. And there are h by 2 plus 1 such terms, because the first index was I equal to 0. The index of the middle term is I equal to h by 2. So starting from 0, ending at h by 2, there are a total of h by 2 plus 1 terms. We can make this, to simplify our calculation, let's drop one of these terms so that we get exactly h by 2 terms. So if we drop one of these terms, we will have exactly h by 2 terms, and we'll get something even less than this series. So this is greater than or equal to 1 by 2 to the power k times log to the power k of n, and so on, with one term short. So ending with one term less than this series. So by cutting off one term, we're getting something even smaller than this series. And let's ignore these smaller terms completely. Let's just drop them. So by dropping the smaller terms, we are reducing the value of this whole series. By replacing all these arguments by the argument in the middle term, we are further decreasing the value of this series. And this is the series that we get as a result of that transformation. And again, we are dropping one of the terms here to get an even smaller series. Now the value of this series with h by 2 terms is nothing but 1 by 2 to the power k times log to the power k of n multiplied by h by 2, because the same term is appearing h by 2 times. The same term is appearing h by 2 times. So we multiply h by 2 with the value of the repeating term, which is 1 by 2 to the power k times log to the power k of n. So this 2 combines with 2 to the power k and we get 1 by 2 to the power k plus 1. And we replace h with log n, because h is log n. The height of the recursion tree is log n. So we get a log n multiplied with log to the power k of n, and both these combine to form log to the power k plus 1 of n. Now note that k is a constant. This means 1 by 2 to the power k plus 1 is also a constant. So this can be written as some constant multiple of log to the power k plus 1 of n. So effectively we've proven that this series or this summation is greater than or equal to some constant multiple of log to the power k plus 1 of n. Right? This series is greater than or equal to this cut down series, the value of which is some constant multiple of log to the power k plus 1 of n. This means that we can take this value, some constant multiple of log to the power k plus 1 of n, and replace this entire summation by that lower bound. Right? We've proven that this series is bounded from below by a constant multiple of log to the power k plus 1 of n. So let's take this lower bound and replace this series by the lower bound. By doing so, we will be reducing the value of this expression. So it will become further less than t of n. So t of n will be greater than or equal to this first term plus c1 times n to the power log base b of a multiplied by some constant multiple of log to the power k plus 1 of n. And that's what I've written here. So this is the lower bound that we came up with. Now if t of n is greater than or equal to this term plus this term, it must be individually greater than this term. So we can drop this term. We can drop this term and get an expression which is even less than or equal to this combined expression. So t of n, which was greater than or equal to this expression, will definitely be greater than or equal to the second expression by itself, which can be written as some constant times n to the power log base b of a multiplied by log to the power k plus 1 of n, which we get from here. So we have proven that t of n is bounded from below by a constant multiple of n to the power log base b of a times log to the power k plus 1 of n. This means that we have proven that t of n is in big omega of n to the power log base b of a times log to the power k plus 1 of n. So we have proven that this function is also a lower bound on t of n. That is, t of n is bounded from below by a constant multiple of this function. we have already proven that T of n is in big O of this function. We proved that in the previous video. So combining that result with this result, we can now claim that T of n is in theta of n to the power log base b of a times log to the power k plus 1 of n. And this is what the extended version of case 2 of Master Theorem provides as the solution to the recurrence. We go back to the statement of the generalized version of case 2. The solution to the generalized version of case 2 is T of n is in theta of n to the power log base b of a times log to the power k plus 1 of n. And that is exactly what we have proven. So our proof is now complete. We proved an upper bound on T of n and we proved a lower bound on T of n. So in effect we have proven that this function is a tight bound on T of n. So to summarize what we did in this video, we proved that T of n is in big omega of n to the power log base b of a times log to the power k plus 1 of n, after proving in the last video that T of n is in big O of the same function. So in trying to prove that this function T of n is in big omega of this function, we started off with the expression for T of n. We used the given information that f of n is in theta of n to the power log base b of a times log to the power k of n, which is what the generalized version of case 2 of Master Theorem says about the relationship between f of n and n to the power log base b of a. F of n is in general n to the power log base b of a multiplied by some power of log n, which could be 0, but in general could also be greater than 0. So using this tight bound, we obtained a couple of inequalities claiming that f of n can be sandwiched between two constant multiples of this function, and we focused on the first of those inequalities, which only talks about a lower bound on f of n. So f of n is bounded from below by a constant multiple of this function. And why did we focus on a lower bound? Because we could take this lower bound and replace this f of n by b to the power I by its corresponding lower bound. And by doing so, we got T of n is greater than or equal to this expression, with the lower bound replacing f of n by b to the power I. And we did this because we ultimately want to prove something of this form. T of n is greater than or equal to some constant multiple of this function. So effectively we had to simplify this summation and show that we can actually get something like this from it. N to the power log base b of a was obtained by simply pulling it out from this summation. And these two terms cancelled out in the summation and we were left with just log to the power k of n by b to the power I inside the summation. So our job reduced to trying to prove that this is greater than or equal to some constant multiple of log to the power k plus 1 of n, because That's what was missing. We already obtained this over here. So in trying to prove that this was greater than or equal to some constant multiple of log to the power k plus 1 of n, we focused only on the first half of this series. We focused only on the first half of the series by cutting the series at the middle term. The middle term was log to the power k of n by b to the power h by 2, which we simplified to this value, which looks similar in form to what we want, except for a missing log n factor. But by focusing on the first half of the series and by reducing the values of the arguments of every term in the first half to n by b to the power h by 2, we obtained h by 2 copies of this same term, and we lowered the value of this whole series even more by that. So this whole series was greater than or equal to h by 2 times the value of the middle term, which was 1 by 2 to the power k times log to the power k of n. And all these terms now have identical values as the middle term because of the reduction in their arguments. And this then simplified to log n times log to the power k of n times some constant. H was log n, so that's how we got an extra power of log n here. And thus we obtained the form that we wanted to prove over here. So this summation is bounded from below by a constant multiple of log to the power k plus 1 of n. And from then on it was easy to prove that if that's true, then we can replace the summation by its lower bound and get something that is even less than t of n. And because this was a lower order term compared to this higher order term, we could just drop the lower order term and get something even smaller. So this is just the second expression here, which can be written as a constant multiple of n to the power log base b of a times log to the power k plus 1 of n, which then proved that t of n is in big omega of this function because it's bounded from below by a constant multiple of this function. And then, having proven the big omega part and having proven the big O part in the last video, we proved that T of n has this asymptotic complexity as stated by the extended version of case 2 of Master Theorem. So this is the proof of the extended version of the case 2 of Master Theorem.